So let me walk you through this phone problem where this phone is accelerating to the left against the seat of this car. On this force diagram, the first thing I drew is the force of gravity. I realized that the phone had mass and it was being pulled down by Earth's gravitational field, so that mg is downwards. The phone isn't accelerating vertically though, so it has to be supported by something. It turns out that something is the grip of the seat. The seat actually pushes it upward, and that is a frictional force. And in this problem, it is static friction that is supporting that phone. The seat also pushes it to the left and provides a normal force. Normal forces are perpendicular to surfaces, and our seat is the surface right here. So the normal force would jut out this way. Looking at this picture, it explains exactly what's happening with the phone. Balanced forces vertically, because the phone isn't accelerating vertically, but it is accelerating horizontally. In that video, it looks like the phone is standing still, but to an observer outside of the car, you would definitely see that this phone is accelerating. The camera in the phone, or in the film that's videoing this, is also accelerating, and that explains why this phone is accelerating. To figure out the coefficient of static friction, I used three big ideas. I realized that the maximum force of static friction is equal to mu static times normal force. I realized that Newton's second law is true horizontally, and I realized that Newton's second law is true vertically here. And since we have balanced force, since we're not accelerating vertically, we have balanced forces vertically. With those ideas, I first started off and said, all right, well, horizontally we are accelerating with 11.76 meters per second squared. That's just an acceleration of 1.2 g, and if g equals 9.8 meters per second squared, then this is 11.76 meters per second squared. The only horizontal force was the normal force, pushing to the left, and divided by the mass of this phone. I then realized, though, I didn't know the normal force. I wasn't sure what it was, but I knew where I could find it using this idea about static friction. I realized that the static friction is equal to the force of gravity, and this was the maximum static friction. At this acceleration, the phone is just barely able to stay on the seat. So this must be the maximum amount of friction. It's like at that acceleration, it's just barely staying on the seat. Any slower, the phone would start to slip down. So, since that's the maximum force of static friction, and that's equal to the force of gravity, I took this and said, all right, well, that's the coefficient of static friction times normal force. That's just a true formula, always true. And this is also a true formula, force of gravity equals mg. I solved for normal force and put that into this formula right here, and then kept on working. Normal force was equal to mg divided by the coefficient of static friction. And then that simplified, and I eventually got a value that the coefficient of static friction was 0.83. I'd expect this surface to be pretty grippy. That phone has a sticky looking case and those seats look to be leather. So that's in the range that I'd expect that to be. And it's a number that doesn't have any units, so the math checks out. Going on forward with this problem, there's some interesting things we can see based on the math we've already did. If the acceleration was any lower, it would mean that there wasn't as much horizontal force. If there isn't as much horizontal force, that means there won't be as much normal force, which means there won't be as much friction. And if friction is smaller, then this phone would start to accelerate down. If the normal force was bigger, that'd be totally okay. There could be even greater amounts of friction, and all that would happen here is the phone would still be okay, and the friction just wouldn't be at its maximum. It could be at some other value. Because the force of static friction is less than or equal to mu static times the normal force. This is only just that biggest value. And lastly, part E says, well, what would happen if we used a tablet that was 3 times as massive? The problem would be exactly the same thing. Eventually, the mass just canceled out. And as long as the coefficient of static friction is the same, everything would remain identical, and it would need that acceleration to remain fine. Turns out it doesn't matter about the mass of the object here, because if it's heavier and there's more force pulling down, it also means there's going to be more normal force accelerating the object. So that's that one. Feel free to ask any other questions you have of me today. But that is working through the phone problem.